All right, now we'll look at the RLC series circuit. Okay. So again, you could connect all these in parallel. So for instance, there's many ways to connect those three elements. So okay, so there are several other diagrams. This is the only one we're considering. Okay, we're not considering any of these other ones. So this is a series RLC circuit. So RLC series connection. Okay, that's what we're looking at. All right, so resistor RLC circuit elements connected in series. Again, so what we'll be interested in is two things. Imax is Vmax over Z. So we are interested in the impedance of this circuit, and we are interested in the phase factor. Okay. All right. So the way now you could, using Kirchhoff's rules, you can set up a differential equation for this circuit. Now it turns out it'll be a second order differential equation. And you could solve that, but an easier way to do that would solve it would be, so let me actually set up the differential equation for you guys. Let's, okay. So, okay. So we'll, VI, this is Kirchhoff's second law, and IT, and this is VT. Okay. So the voltage is Vmax, V naught sine omega t. So what we're doing is we're starting at this point and going around like that. Okay. Minus IT over R, and this is minus QT over C divided by C. C is Q over V. Yeah, so the voltage across the capacitor is that, and minus L times di by dt equal to 0. Okay, so to solve the circuit, you'd have to solve this differential equation, and you can solve for I. Okay, and QT, so IT is dq by dt. Okay, so this this equation would be V naught sine omega t minus R dq by dt minus Q by C minus L times d square Q by dt squared. Okay, so there is the second order differential equation you would have to solve for. Okay. So rather than solving this differential equation and you'd solve for Q and then get I from taking the derivative of Q. Rather than doing that, we'll show you how to solve this using phasors. Okay, so let's look at the phasor for, okay, so there is the RLC circuit. And here's what we do. Okay, so here's the current vector, current phasor. For the inductor, the voltage is ahead of the current. For the capacitor, the voltage is 90 degrees ahead of the current. And okay, so resistance, I'm going to decrease the capacitance. Oops. Okay, and okay, so there you go. So there's the voltage, there's the current. The voltage across the inductor is 90 degrees ahead. The voltage across the capacitance is 90 degrees behind. And the voltage across the resistor is in phase. Okay, so what we do is for the voltage amplitude, you just take the vector sum of the two. So the Y component of the voltage is VL minus VC, and there is the total voltage. The Y component of that is VL minus VC, and the X component is equal to the X component is unfortunately this the amplitude of the current and the voltage are the same, so the vectors are right on top of each other. So the X component of the voltage vector is the voltage across the resistor. Okay, so here's the total voltage, and that's what we'll see. Okay, so to figure out those two things, here we go. So the maximum voltage, this amplitude is X component of the voltage times square times Y component of the voltage square. So voltage across the resistor plus VL minus VC square. This voltage is I max times R, and this voltage is I max times XL. This voltage is I max times XC square. I is common, you can pull out. Okay, and so so the voltage amplitude is I max times Z. Okay, so Z is the generalization of the impedance. So voltage is I max times Z, and Z is R square plus XL minus XC square. Okay, so let me go to the chalkboard. Okay, so you see from this, you can see that V naught equal to, here is, this guy is I max, okay, or you can call it I naught, is I naught times Z, okay. And that's what we've done here. So V max is I max times Z, okay. So there is Z, okay. So what we are saying is for this circuit, the resistance or the impedance of this circuit is that R square plus XL minus XC. So Z is R square plus XL minus XC. Okay, and the phase angle will this phase angle will turn out to be equal to, there's the Y component. And so there's the Z vector, there's the Y component of the Z vector is XL minus XC, and the X component is R. So this phase angle is tan inverse of XL minus XC divided by R. Okay, so what we were interested in was, we were interested in two quantities for this circuit, Z and phi, and here they are. So Z is square root of R square plus XL minus XC square, and phi is tan inverse of XL minus XC divided by R. Okay, so those are the two things we were interested in, and there we have it. All right, so now this table just lists, if for a series combination for these elements, it lists these two values that we are interested in, Z and phase angle phi. So that's how important these things are. You can even find tables for them. Okay, so for a resistance, the impedance is just R and the phase angle is 0. For a purely capacitive circuit, the impedance is 1 over omega C, X, which is XC, and the phase angle is minus 90 degrees, okay? So the voltage is 90 degrees behind the current. For the inductor, it's XL, which is omega C, omega L, and the voltage is 90 degrees ahead of the current. For for a resistor and a capacitor in combination, there's Z, and the phase angle is between 0 and 90 degrees, minus 90 degrees. For this guy, it's plus between 0 and 90 degrees. Okay. And when you have all three in combination, there's a Z, and if XC is greater than XL, then it's a capacitive circuit, and if XL is greater than XC, then it's an inductive circuit. Okay. All right, so there are the phase impedance and phase angles for all these combinations. Okay. All right, so now we'll look at the power delivered to the RLC circuit. So there's the RLC circuit, and we're going to see how much power is being delivered to the circuit, meaning how hot is this cooking? The more power it's delivered, the more stuff is being done. Okay. And if no power is being delivered, nothing is cooking. Okay. All right, so power is the instantaneous current times the instantaneous voltage, which is so I max times sine omega t minus phi, and V max times sine omega t. Okay. So the average power is I max, V max, and you can take the average of these two functions over a cycle. Okay. And the average will work out to I max, V max over 2 times cosine phi. And this is the power factor. And we'll remember IRMS was I max over root 2. So this expression is I max V max over 2 is equal to IRMS times VRMS times cosine phi. Okay. So cosine phi is known as the power factor. So if this was 90 degrees, this would be 0. No power is being delivered. Okay, so let's go back to the table. So when it's a purely capacitive circuit or a purely inductive circuit, phi is plus or minus 90, and no power is being delivered. Okay, so if you connect a pure capacitor or a pure inductor to an AC source, all that happens is on one cycle, energy is stored in the capacitor, and then in the next cycle, it's returned to the source. So no net power is delivered. So if you have a purely capacitive or a purely inductive circuit, no cooking will happen. Okay, nothing will get cooked. Okay. So that's what this expression tells you. Okay, so the power factor is important. Okay. So no. Well, in fact, let me show you the power factor. So here's a power plant, and here's a city. Power is delivered via transmission lines, and you see these transformers on poles near your house and stuff like that. Okay, so imagine that this is a city. It turns out that these power lines will have inductive impedance. So what they do is outside the city or at the end of the city, what they'll have is they'll have power capacitors which cancel the inductive capacitance, and then you have a total net of just pure resistance to the city, and that's when the maximum power is delivered to the city. Okay, so that's what this is. All right, so actually I will pause now before we get into the next topic, and I'll let you guys